Friend, yesterday we talk about the bond energy. Okay, then now we have to talk about the bond dissociation energy. It is nothing but the energy required to break the bond in the given molecule AB, or say radical or ion, and thereby gives rise to two fragment A and B, which may be free radicals, ions, or atom. Bond dissociation energy are very sensitive to differences in the electronic and the atomic configuration, because such a differences such a differences greatly affect the forces between the atoms. Hence, for the bonds between a given pair of the atom in a different molecule, or for a radical, first dissociation energy may differ appreciably. There will be MCQ on the bond dissociation energy. The energy required to break the bond in the given molecule is called as the bond dissociation energy. It is very sensitive to differences in the electronic and atomic configuration, or say it is depend upon the electronic and atomic configuration. Okay, this is the bond dissociation energy. If the one bond is bringing, that energy is given here. You can see on the summation you will get a total energy for this particular CH per molecule. Then resonance energy, the difference between the delta HA, enthalpy of atomization, that we have seen, and the sum of the mean bond energies for the most probable structure is called as resonance energy of the molecule. It is a measure of the stabilization of the molecule. Resonance energy is resonance energy is the measure of of molecule stabilization, or say is a measure of the stabilization of the molecule. ER is equal to delta HA minus summation EAB. That is all the bond is that is summation of the mean bond energy is given. Benzene is given. Example is here. You can go through this particular thing. Okay, but here just we have the MCQ. That's why I am only highlighting on the MCQ. Then Kirchhoff equation. That equation is very much important. That may come in the equation. That equation, final equation, is the delta H2 minus delta H1 is equal to delta G in bracket T2 minus delta Cp in bracket T2 minus T1. This is known as the Kirchhoff equation. It is used to calculate the enthalpy at temperature T2 by knowing the delta H1 at temperature T1 and delta Cp, and vice versa. Okay. Consider now here it is a general reaction. AA plus BB gives you the QQ plus RR, where capital letters for the individual substance, small letters for the number of moles of the corresponding substances. These reactions has extensive property which changes during the chemical reaction. If HA, HB, HQ, these are the molar enthalpies of that particular substance, then react for the enthalpy for the reactant side is given by AHA plus BHB, and for the product side it is given QHQ plus RHR. Okay, if the reaction goes to completion, the initial states correspond to the reactant, and the final states correspond to the product. The enthalpy change of the reaction is given by delta H is equal to H product minus H reactant. Then you can substitute this on taking the partial differentiation with respect to the temperature at the constant pressure. You will get the delta H divided by delta T at constant P is equal to is equal to Q in bracket dHQ by dt at constant P plus R divided by dt at constant P plus dot. Now the minus will be there. Minus A delta HA dt at constant P minus B delta HB dt at P. This is the equation you will get. After this, delta Cp is equal to delta H by delta T at P. That is nothing but the molar heat capacities at constant pressure is nothing but a delta H by delta T at constant pre. It is nothing but, therefore delta Cp is equal to that equation. On comparing this equation, you will get delta H by delta H by delta T at constant P is equal to delta Cp, and therefore delta H is equal to delta Cp divided by into delta T. On integrating this equation, we will get this equation. delta H2 minus delta H1 is equal to delta Cp in bracket T2 minus T1. This equation is nothing but the Kirchhoff equation, and it come for the MCQ. Okay, this is about your MCQs. Probable MCQ will be there on this formula. Then numerical is based on this particular Kirchhoff equation is there. You can go through this numerical also. Very simple. You have to first of all heat up reaction for this particular reaction is given. That reaction is nothing but the nitrogen plus the hydrogen gas gives you the ammonia at 27 degrees centigrade is minus 92.0 kilojoule. What will be its value at 60 degrees centigrade? The molar heat capacity is at constant pressure and 27 degrees centigrade for nitrogen, hydrogen and ammonia are the molar heat capacity is at constant pressure at 27 degrees centigrade at constant pressure and 27 degrees centigrade. For the nitrogen 285 is given, I think so. See that value. Okay, $285. 28.5 I think so it is. Then the 28.3 and the 37.0 joule per Kelvin per mole is there. Okay, then you can take this delta Cp is nothing but the total heat capacities minus sum of the heat capacities of the reactant, total heat capacities of the product minus sum of the heat capacities of the reactant. Reactants are the two things, nitrogen and hydrogen is there. Okay, you can write this particular twice ammonia is here, total heat capacity of the product. You have to multiply with the 2, and then here this is a 28.5 plus thrice into that value. Delta Cp is that value. Once you got the delta Cp, then you can calculate delta H, means heat of reaction at the temperature 60 degrees centigrade. You can easily calculate. Please go through this example. Very simple it is. Here you have to write the given things. Okay, T2 is given, T1 is given, delta H is given, delta H1 is given, right? T2 minus T1 you can take. Delta Cp how you can calculate, that is shown over here. Okay, please go through this. If you have any doubt you can ask freely. Thank you.